We've shown that the clique tree algorithm has some pretty cool properties, that it guarantees that we achieve the correct marginal at every single clique, and therefore that these marginals necessarily agree with each other. We've also seen that these marginals can be computed using a single upward and downward pass over the clique tree, so a fairly efficient computation. But we also know that the problem of inference in probabilistic graphical models is an NP-hard problem, and so somewhere over there must be a catch. That is, there must be a computational cost that occurs at least in certain cases when we run the clique tree algorithm. And what we're going to do now is we're going to try and understand where that hidden cost might lie.
So, what we're going to do, so in order to analyze the computation complexity of a clique tree, we're going to define a little bit of notation. So let's consider an edge, ij, in the clique tree T, and let's define a little bit of notation. We're going to divide the variables into three groups. There is this group, so here what we have is a clique tree. Here's Ci and Cj. They're adjacent cliques and they're connected to each other via a subset Sij. And then there's this whole clique tree, a whole bunch of cliques on the left side and a whole bunch of cliques on the right side. We're going to divide the variables into these three groups. W that's on the I side of the ij edge are the variables that are just in this group here, not counting the subset, which is going to appear on both sides. W that's on the j side is over there, and Sij is the stuff that's in the middle. So these are three mutually exclusive and exhaustive groups that partition all of the variables in the tree. And now here's an interesting and a quite enlightening theorem that says that the clique tree T satisfies the running intersection property if and only if, for every subset ij, we have that the variables on the left side of the edge are independent of the variables on the right side of the edge, given the variables in the middle of the edge. That is, these variables, the subset, separate the left side from the right side. Now, remember that the running intersection property was the critical property that we used to prove correctness of the clique tree algorithm. And so this is coming up with this condition that tells us exactly when running intersection holds is important because this is the defining property for all of those nice behaviors that we talked about earlier in terms of the clique tree algorithm.
So let's try and convince ourselves of this by looking at a concrete example first. Let's look at the clique tree that we have over here, and let's, for example, focus on this subset, which has the variables g and s. And the variables on the left side of that subset, excluding the variables g and s, are I, D, and C. On the other hand, the variables on the right side of this subset, again excluding g and s, are H, J, and L. So now let's look at where these variables place themselves on the graph structure over here, which is the induced graph corresponding to the Markov network, which we derive from the factors in this Bayesian network. So Bayesian network CPDs produce factors. The factors give us this induced Markov network. So where are the subset variables G and S? Those are over here. Where are the variables on the left-hand side? These are the blue variables CID, and they're sitting over there. And the green variables, H, J, and L, are sitting over here. And a simple inspection can show us that there are no paths or trails between the blue variables and the green variables that do not go through the red variables. So that we conclude from that the variables C, I, D are separated from H, L, and J given G and S. And from the connection between the graph structure and independence in Markov networks, we can conclude from that that this independence property holds. That is, that C, I, and D are independent of hj and L given G and S, which is exactly what we wanted to show, that the subset separates the variables on the left, the blue variables, from the variables on the right, the green variables.
Let's try and give a slightly more general argument for this, one that isn't just demonstrating it in the context of a particular example. So let's ignore for a moment the concrete letters inside this example and just think about why this is going to be true. So let's imagine that this is now a generic subset, and this is it over here. And we'd like to prove that all the variables on the green side are independent of all the variables on the blue side. So let's assume otherwise. This is going to be a proof by contradiction. If this were not the case, then that means that in this induced Markov network, there needs to be so assume otherwise. Which means there needs to be a path in the induced Markov network between the blue side and the green side. So between W less than ij and W less than ji. Well, if there exists a path that goes from one side of this graph to the other, it means that there eventually has to be an edge where one node is on one side and one node's on the other. That means there needs to be some edge that goes from the blue side to the green side. Now notice, as I forgot to say, this path that exists in the induced Markov network doesn't go through the subset, because otherwise the subset would separate it. So it doesn't go through Sij. So there needs to be an edge that goes, for example, from here to there. Or it doesn't matter which node I pick, which pair of nodes I pick. There needs to be some node on the green side and some node on the blue side. This is the green side, and this is the blue side, and an edge that goes between them that doesn't go through the subset. But now that implies that there needs to be some factor phi that involves those two variables. So in this case, C comma H. But now because of family preservation, that factor must sit in one of the cliques in this clique tree. And that clique is either on the green side or on the blue side. Has to be somewhere. So let's assume that we put that clique without loss of generality on the green side. But now what happens? We have an H that's sitting here. And remember, H is a blue variable. And H is also sitting here because it's on the blue side. And now we have an H in one clique and an H in the other, and running intersection property tells us that H needs to be everywhere in between, and specifically, it needs to be in the subset, which is a violation of the assumption, either of the running intersection property or of the assumption that the variable H is not in the subset. And so that's sort of a somewhat formal proof outline that can, with a little bit of extra effort and notation, be made into a rigorous proof of why running intersection property implies this independence assumption. And I didn't prove the other direction because this is actually the direction that we care about more. So we started out this whole discussion by saying that these properties have computational implications. But where are these computational implications? What can we conclude from the fact that the subset needs to separate the graph into two conditionally independent pieces? Well, it turns out that in many graphs that implies a certain minimal complexity that can sometimes be quite large. So let's look at this in the context of two quite simple but very commonly used examples. So here is an example of what's called a complete bipartite graph, where we have two sets of variables that have no edges between each of the sets separately, but where all of the cross edges are present. This is a structure that is that we've actually seen before. We saw it in the context of the plate model for course difficulty and student intelligence, where we had a bunch of difficulty variables, a bunch of intelligence variables, and there were no edges between the difficulties or between the intelligences, but for every difficulty intelligence pair, there was an edge that was induced by the V structure corresponding to an observed student grade between the course difficulty, corresponding to that course difficulty and that student intelligence. So what is the smallest subset that we could possibly construct for this graph? Can we, for example, look at just say these two A's and separate out the graph into two conditionally independent pieces? Well, no, not really, because, for example, if we now look at these two B's, we can see that you can connect them via any one of the other A's that I didn't include in the subset. And so this doesn't decouple the graph at all. With a little bit of extra thought, it's not difficult to convince oneself that the smallest subset that we could construct that actually breaks up the graph into meaningful pieces is either all the variables on the one side or all of the variables on the other, which means that the smallest subset, or in any kind of meaningful clique tree, has size greater than or equal to min of k comma m, where k is the number of variables on the one side and m on the other. A slightly less obvious example, but one that is also imposes some very significant lower bounds, is in the context of a grid, such as we encountered in the context of the Ising model, or when doing image analysis where the variables correspond to pixels. And now let's try and think about how we might break up this graph into conditionally independent pieces. Now, we can construct clique trees that have smaller subsets, small subsets. For example, here's a subset that breaks away A11 from everything else. But notice that that still leaves me a very large everything else. But if we try, for example, to break up the graph so that A11 appears on the one side and A44 appears on the other, any clique tree that you give me that will have this separation with A11 on the one side and A44 on the other, any such clique tree has to have a subset of size greater than or equal to n, where this is an n by n grid. Which means that if you try and break up the n by n grid in a way that puts one corner on one side and one corner on the other, then you're going to have a subset that's at least a dimension of the grid. And breaking it up in other ways doesn't make it any better. So here are two cases where we can place a lower bound on the size of the subset that is required for running clique tree inference. And that is where we pay the exponential blowup that is in some sense required by the fact that, that the problem is intrinsically an n problem. So to summarize, we've shown previously that the correctness of the clique tree inference algorithm relies on having the running intersection property. And we have now shown in turn that the running intersection property implies certain separation properties on the original distribution. These separation properties, in turn, can be used to analyze the complexity of inference in different graphs and provide certain minimal bounds on the complexity that would have to be incurred by the best possible clique tree on graphs. And we've already seen before a notion of minimal complexity, which is the minimal induced width of the graph. This notion is a little bit different because it talks about subsets, whereas the induced width really talks more about cliques. But these are both different ways of analyzing the complexity, a certain minimal complexity that has to be incurred by exact inference, which again is related to the anti-hardness of the problem.
We previously used the variable elimination algorithm as a way of proving the correctness of the clique tree algorithm. It turns out that this relationship can also be used to answer another fundamental question regarding clique trees, which is the question of where clique trees come from, or rather how we might construct a good clique tree. In order to do that, what we're going to do is we're going to look at a run of variable elimination, and we're going to see how we might reinterpret it as a clique tree run.
So in order to do that, let's look at the variable elimination algorithm and try and take a clique tree view of what it's doing. So the variable elimination algorithm, as a reminder, starts by, takes a series of steps where in each step it creates a large factor, which for the purposes of this discussion we're going to call lambda I. And what it does, and it does that by taking a bunch of factors and multiplying them together. When that is done, we eliminate a variable from lambda I, and that gives us a new smaller scope factor, which we're going to call tau I. And tau I is put into the pool of factors that we have available to us, which means that at some point we're going to use it in the context of computing another large factor, lambda j, when we multiply a bunch of factors together. So now let's think about this process in terms of passing messages in between computational entities in the same way that we had when we were doing message passing algorithms. So we're going to look at these intermediate factors, lambda i's, as the cliques in a clique tree. And the tau i's that are used, that are produced in the context of one clique and utilized by a different clique, we're going to consider that to be a message. So these little factors that are produced by one lambda and consumed by another lambda can be viewed as a message that's passed from the clique that corresponds to the first lambda and received by the second lambda. So summarizing, the variable elimination algorithm defines a graph. We're going to have a cluster Ci for every factor lambda I, and we're going to draw an edge between Ci and Cj if the factor that was generated in the computation in which I multiplied together all the factors to produce lambda I is used in the computation of lambda j. And so we can think of it as Ci, which corresponds to lambda I, passing a message to Cj that corresponds to lambda j, and that message is the tau I that was produced by the lambda I computation. So now let's look at this in the context of an example. We're going to go through the variable elimination process that we had for our network that we had earlier, the enhanced student network. And so the first variable elimination step multiplies together the C factor and the CD factor. And that gives us, this is my lambda 1. And lambda 1 produces a clique whose scope is CD, and so that's this clique over here. The next step eliminates D, and the way in which it does that is it takes tau 1, and then it multiplies that by one of my original factors, phi g, and so now we have a lambda 2, this is my lambda 2, and that gives me a clique whose scope is GID, and since GID used tau 1, then we have an edge from CD to GID, whose scope is the variable D. The next step in the analysis that we did before eliminated the variable I, and again used two of the original factors, phi I and phi S, and it also used tau 2. And so now we have a factor lambda 3, whose scope is G, S, and I, because those are the variables in this scope over here. And the message, GI, is that we see here, this edge between GID and GSI corresponds to this tau 2 that was produced by lambda 2 and consumed by lambda 3. The next elimination step didn't use any of the factors produced by other cliques. It just used one of the original cliques, so it just used phi H. And so notice that it's currently not connected to anything. It's just sitting there all by its lonesome. And the next step now gets to use factors that were produced in two separate computations. So notice that this computation for lambda 5, which is this guy, used both tau 3 and tau 4, which is why we have both an edge from cluster 3 and an edge from cluster 4. The next step that we took marginalized out S. It multiplied in tau 5 and one of the original factors, JLS. And so now we have a message here that's passed between cluster 5 and cluster 6. And finally, there was the marginalization of L, and so we have a JL cluster. Now, if you look at this graph, at this clique tree, you'll notice that it's bigger than the clique tree that we had for this network to begin with. And the reason for that is that we actually have 3 adjacent cliques where one is a subset of the other. So JL is a subset of JSL, which in turn is a subset of GJSL. Now, if you think about it, there's really no point to including 3 cliques where one is a subset of the other, because you might as well do all of the computation in the first clique to begin with. There's no value to sort of breaking it out into separate data structures. And so a typical post-processing step is to then go ahead and remove redundant cliques and just basically collapse them and their factors into the biggest cliques that subsumes them. So in this case, since we had phi JLS, which originally was utilized in tau 6, we're now going to move that and put that instead in, sorry, it was used in lambda 6, we're now going to stick that into clique 5. And so we've seen how we can take a variable elimination process, a run of variable elimination, and use that to produce what looks like a clique tree. But is it a clique tree? So what properties can we prove about this output from a variable elimination run? Well, first is the fact that it is, in fact, a tree. If we want it to be a clique tree, it better be a tree. Why is it a tree? Because in variable elimination, every intermediate factor tau, once you produce it, it gets consumed exactly once. Once it gets consumed, remember in the variable elimination algorithm, it gets taken out of the set of factors and then it disappears because it gets multiplied in. And so if you think about this as a directed tree, it starts out and it produces factors, and each factor feeds up into only a single other parent. And so as a directed tree, it means that every cluster has at most one parent. And in fact, every cluster except the last one has exactly one parent, because eventually everything has to be consumed because everything is multiplied together. And so this variable elimination process induces a directed tree where we subsequently forget about the directionality of the edges. The second property that is, again, not difficult to show is that the tree is family preserving. And that is because each of the original factors was in my original factor set. Each of my original factors, phi, in my original factor set, big phi, was somewhere in the variable elimination process. And that means it must have been used at some point, because eventually I'm multiplying all factors together. And therefore, it must be contained in the scope of one of the, sorry, this should be lambda I. And that lambda I, by force, has a scope that contains the scope of phi, which is what we need for the family preservation property. The final property that we had that we would like to show holds is that the tree respects or obeys the running intersection property. And so as a reminder, that property says that if you have two clusters, Ci and Cj, with a variable x that is present in both, then x needs to be in each cluster and each subset in the unique path between Ci and Cj. So first of all, let's convince ourselves that that running intersection property holds here. And we've already seen that because this is actually the familiar clique tree that we had for this example. In fact, we produced that clique tree by running variable elimination using exactly the process that I showed you before. Now let's show that, however, more generally. So we want to prove to ourselves that if T is a tree of clusters that was induced by a run of variable elimination, then T obeys the running intersection property. And so now remember that this tree came from a directed run. And so what I'm showing you here is actually a directed tree where we see how the cluster is communicated. This is not the same tree that we had in our example. It's a more complicated one to illustrate the sort of to make the theorem a little bit more interesting to show. So in one of those subsets, and in exactly one of those subsets, the variable x is eliminated. Because this is a run of variable elimination, every variable is eliminated exactly once. So let's imagine that x is eliminated here. So this clique over here is the last to see x, so C4 has x in it. X is in C4 and x is not in C6. Now let's take any other cluster that contains x. So, for example, assume that cluster 7 contains x. Well, if cluster 7 contains x, and x wasn't eliminated on this edge, because it's eliminated exactly once, it means that it needs to be on the subset, which means it was in the message tau that C7 produced. So it's in tau 7. X is in the scope of tau 7, which means that x also needs to be in the scope of C3 because it was multiplied in. If it was multiplied in, then it has to be in that scope. And so by continuing this in exactly the same inductive argument, we know that since x has to be in C3, it also needs to be on this subset, and so on. And so we've shown that x needs to be on the path from C7 to C4. And now let's take a different cluster that contains C5, it contains x, for example, C5. We can similarly show that x needs to be on every step along the path. And since this is a tree, it means it needs to be on the path between C7 and C5. And so that argument shows that for any pair of clusters or cliques that contain x, x has to be on every step of the path between them. So to summarize, a run of variable elimination implicitly defines a correct clique tree, which means that you can, if we want to get a clique tree that has the required properties, family preservation and running intersection, we can simply simulate a run of variable elimination. What does it mean to simulate? It doesn't mean that we run variable elimination because that would be an expensive process. We just figure out what factors I would multiply and what scopes they would have, and therefore, and what factor gets used where, and that gives me the cliques and the connections between them. And this is the exact process that we did in the simple example that we had. And that clique tree has a computational cost which is essentially equivalent to the cost of running the variable elimination algorithm. Because if you think about the sizes of the cliques that are produced, they correspond exactly to the sizes of the factors produced by variable elimination. So these costs are directly comparable to each other. Except that as we showed before, the clique trees use dynamic programming or storing or caching of the messages so that we don't need to recompute the same message more than once. And that allows us to produce marginals over all of the variables in the network and only twice the cost of running variable elimination. So taking yet one other step backwards, what that means is if you care to get the values of the marginals for even, not necessarily even all variable, but multiple variables, one efficient way of doing that is to take variable elimination, do the simulation to figure out what clique tree we want to build, or how to build a clique tree, and then use that clique tree to compute all of the marginals by appropriate message passing. And we talked about variable elimination and how to use heuristic solutions to construct a good variable elimination ordering, one that gives us relatively small factors hopefully along the way. And that exact same set of heuristics is also useful for constructing a small, efficient clique tree to the extent that that's possible given our graph.
The belief propagation algorithm, when run over a general cluster graph, is an iterative algorithm in which messages are defined in terms of previous messages. And we said before that when run over a general cluster graph, the algorithm might not converge, and that even if it converges, it might not get to the right answers. What we're going to talk about now are how bad these problems are and what are some of the tricks that we use in practice in order to improve the behavior of this algorithm in these two different regards.
So let's get some intuition by looking back at our misconception example. This is not actually our misconception example. It's one where we modified specifically the potential phi 1ab to make the behavior even more extreme by making these potentials larger so that there is a stronger push to agreement between A and B. So A and B really, really prefer to agree. And what happens in this example? We can see this beautiful oscillatory behavior of the belief propagation algorithm. So the x-axis is iterations of BP, and this is some notion of distance to the true distribution, to the true marginals. And why do you have such strong oscillations? Let's look at what these potentials are doing. So this potential over here pushes A and B to agreement. And so as you pass this message, A and B want to agree. A and D also want to agree. B and C want to agree. But C and D really want to disagree. And so as messages are passed, you're getting conflicting messages from both sides. D, for example, on the C side, C keeps pulling at it to agree with it. Sorry, to disagree with it. On the other hand, when you go all the way around the loop, C is actually urging D to agree with it. And so from the one side, you're getting a pull for C and D to be the same. And from the other side, you're getting a pull for them to be different. And this sort of, this conflict over the cycle, over the loop, causes this oscillatory behavior as messages are passed from one side or the other. This type of configuration of specifically tight loops, strong potentials, and conflicting directions is probably the single worst example or the single worst scenario for belief propagation. This is the case where it's going to do the worst in terms of both convergence and in terms of the accuracy of the results that are obtained. Now, in this example, ultimately, you actually do get convergence. You can see it takes about 300 iterations, but ultimately you get convergence. 300 is a lot for a graph this size. Here is one that up to 500, you didn't get convergence at all. Now, maybe if we ran it for 10,000, it might converge, but it's hard to say. And so how do we improve the convergence as well as the accuracy properties of the network? So first, let's look at what not to do. Here is the most important thing not to do, which is a variance of belief propagation called synchronous belief propagation. In synchronous belief propagation, which was actually one of the most commonly used variants at the very beginning of the use of the BP algorithm, all messages are updated in parallel. So all of the processors wake up, so all the clusters wake up, they look at all of their incoming messages, and they compute all of the outgoing messages all at once. Now, this is a great algorithm from the perspective of simplicity of implementation and also from the ability to parallelize, because you could assign a processor to each of the cluster and they're all working in parallel and there's no dependencies between them. Unfortunately, synchronous belief propagation is actually not a very good algorithm. And so what you see here is the number of messages that have converged as a function of the amount of time spent. This is an icing grid with certain parameters, it doesn't matter. And you can see that, there is a certain improvement over time, and then it kind of asymptotes at the certain number of messages that have converged. By contrast, let's compare that behavior to asynchronous belief propagation, where messages are updated one at a time. So this one and that one. Now notice that this algorithm is poorly specified because I didn't tell you what order we should do the updates in. We'll come back to that in a minute. But even by the simple virtue of passing messages in an asynchronous way, the behavior improves, both in terms of how quickly we get messages to converge, and in terms of the number of messages that are converged. Now, this is not a particularly good message passing order. Here's a much better message passing order. It takes a little bit longer to get certain messages to converge, just trying to make sure that everything is converging. But notice that eventually, and in not that long of a time, it actually converges to 100% convergence rate. Okay? So here's some important observations regarding this. First of all, convergence is a local property in belief propagation. Some messages converge quite quickly, others might never converge. And when you have some messages that after you run the algorithm for a certain amount of time don't converge, one often simply just stops the algorithm and says, this is what we have and we're done. Synchronous belief propagation has considerably worse convergence properties than asynchronous belief propagation, which is why pretty much at this point, very few people actually ever use synchronous belief propagation. And if you're using asynchronous belief propagation, the order in which messages are passed makes a difference both to the rate of convergence, but even more surprisingly, perhaps, to the actual extent to which messages are ever converge. And so how do we pick the message passing order? There's several different scheduling algorithms. I'm going to present two of the more popular ones. The first is called tree reparameterization, or TRP for short. And what it does is it picks a tree and then passes messages in that tree in the same way that you would do in a clique tree algorithm to sort of calibrate that tree, keeping all other messages fixed. So for example, we might start by calibrating the red tree, which means I pass messages this way and then back in the other direction, keeping all other messages fixed. Now I pick a different tree. I'm going to pick the blue tree. Here's a blue tree. Notice that I can't close the loop because otherwise it wouldn't be a tree. So I can't go all the way back to psi 1, 1. And now I calibrate in the other direction. And I continue to do that by picking a tree and then running it, and then calibrating it. And the only constraints that I need to satisfy is, first of all, that my trees cover all edges. So that's a constraint, because otherwise I'm going to miss a certain message that needs to be passed. And the second is not so much of a constraint, but rather it tends to improve performance if the trees are larger, which means it's good to pick spanning trees, which span as much of the graph as possible without containing a loop. So spanning trees are good. So that's one message scheduling algorithm. The second message scheduling algorithm is something that's called residual belief propagation, and there's actually several variants of that now. And what it does is it tries to look for good messages, messages that are high-value messages. So it looks for two clusters whose beliefs disagree a lot. And if they disagree, that means that if I pass that message, that's going to potentially have a large impact on the receiving clique, or cluster rather. And so I'm going to keep a priority queue of edges, and I'm going to pick the messages from the top of the queue based on how much I think they're going to affect, how much of an effect they're going to have, which is some kind of heuristic notion, potentially, of the disagreement between the two adjacent clusters. The other big important trick that people use to improve the convergence of the belief propagation algorithm is what's called smoothing, or sometimes damping, of messages. And this is a general trick that's often used to reduce oscillations in dynamic systems that are based on these kinds of fixed point equations where the left-hand side is defined in terms of the right-hand side. So here we define delta ij in the original belief propagation algorithm as a function of other deltas. And we've seen that that can give rise to oscillatory behavior. This is just the standard belief propagation message. And what we're going to do now is, instead of that, I'm going to do a kind of smoothed version. So I'm not going to let the message change too drastically. I'm going to have a weighted average where the weight is lambda of the new message, which is this thing, and the old message. And that turns out to, again, dampen oscillations in the system and increase the chances that it converges. So let's look at some example behaviors. So here we see synchronous belief propagation in red over here. And this is the percentage or fraction of messages converged. So 1 would be perfect convergence. We can see that synchronous plateaus at about 20 to 25% of messages converged, which is pathetic enough to be pretty much useless in practice. If only 20% of your messages converged, then really the remaining messages don't really mean very much. Without smoothing is the green line, this one. And we can see that This is asynchronous without smoothing. We can see that even without smoothing, the asynchronous algorithm achieves considerably better performance than the synchronous algorithm. We didn't even show synchronous without smoothing because it would be even worse. And then finally, the blue line is asynchronous with smoothing. And we can see that it achieves perfect convergence at some point. And you can look at behaviors of individual messages, or individual marginals rather, individual beliefs. So here, this is still an icing grid, by the way. So icing grid, which is sort of a standard setup for trying out convergence of various approximate inference algorithms. And so what you see here, the line here, the black line, is the true marginal. And you can see that synchronous belief propagation basically flip-flops around it indefinitely, whereas asynchronous belief propagation converges pretty quickly and very close to the right answers. Not always. This is a different variable in the same model. The black line, again, is the true. And here we can see that, sure enough, asynchronous does improve convergence, but convergence is still to an answer that's not quite right. And you see that behavior, you see both behaviors in real networks. And in practice, depending on all the factors that I mentioned at the very beginning, how tight the loops are, how strong or peaked the potentials, those are going to determine how many of the factors have this oscillatory behavior and how wrong the answers are. So just summarizing, there's two main tricks for achieving BP convergence, damping or smoothing and intelligent message passing. Convergence is often easier to obtain using these tricks than correctness, and convergence, unfortunately, doesn't guarantee correctness. And the bad cases, the ones that negatively impact both of these, are strong potentials that are pulling you in different directions and tight loops. And we're not going to have time to go into all of these topics, but there are some new algorithms that actually have considerably better behavior, both in terms of convergence and in terms of the accuracy of the results. And that is based on a view of inference as optimizing some distance to the true distribution. And there's some really cool ideas as well as math in this, but much of this is outside the scope of this class.
One of the more interesting stories in the field of probabilistic graphical model relates to the connection between the algorithm of loopy belief propagation and the problem of decoding messages sent on a noisy channel. This is a connection that was discovered fairly recently and has proven to have a tremendous impact on both disciplines, that of probabilistic graphical models and that of message decoding.
So let's understand the message decoding problem. Imagine that I want to send k bits across a noisy channel. If I just go ahead and naively send those k bits, then it's impossible for me to know from the noisy bits that I receive at the other end what the correct bits ought to have been, because we don't know which ones got corrupted and which ones didn't. And so what people have developed is the notion of coding theory, where those k bits are passed through an encoder, and what we get at the end are n bits, where n is usually greater than k, and those are the bits that are actually transmitted across the noisy channel to give us a set of noisy bits y1 up to yn, which we now hope to be able to decode in a way that ideally gives us bits v1 up to vk that are close and hopefully completely accurate relative to the bits that were originally sent, u1 up to uk. So that's message coding and decoding in a nutshell. And the rate of a code such as this is k over n. That is, you send n bits of which k are actual information. The bit error rate that one gets, and that's a function of the channel itself, is the overall probability that a bit that we get on this side, say the first bit, what is the probability that the first bit is correct? That is the same as as the original bit. And so the error rate is the total average of the probability that these are different across the k decoded bits. So we can now think about different channels and their properties, and there's this a very important notion called a channel capacity. So let's first think about different error rates that a channel, different error modes that a channel might exhibit. So here's something called the binary symmetric channel, often abbreviated BSC. And the binary symmetric channel says that when I send a 0, then with probability 0.9, I get a 0. But with probability 0.1, I get a 1. And conversely, with when I send a 1, I get a 1 with probability 0.9 and a 0 with probability 0.1. You can see why it's called the binary symmetric channel, because the error is symmetric between 0 and 1. A different error model, or erasure channel, where the bits don't get corrupted, they just get destroyed. Now, the big difference between the binary eraser channel, abbreviated BEC, is that when a bit gets destroyed, I know it. That is, what I get at the end is a question mark, as opposed to a bit where I don't actually know whether that was the original bit that was sent or a corrupted bit. Here I know that the bit was corrupted. And finally, here is what's called a Gaussian channel, where the noise that gets added on top of is actually analog noise. And so there is sort of a Gaussian distribution relative to the signal that was sent. And it turns out that these different channels have very different notions of what capacity means. And capacity will define exactly what implications that has in a moment. But information theorists, they're super smart people, have computed the capacity for these different kinds of channels. And it turns out that, for example, the capacity for the binary symmetric channel is a little bit over 0.5, where the capacity of the binary eraser channel is 0.9, where 0.9 is this probability of getting the correct bit. And if you think about that, it makes perfect sense that the capacity of a channel where you know that bits were erased is higher than ones where you have to figure out whether bits are right or wrong. So this is a less a more benign type of noise. And what you see over here capacity of the Gaussian channel, and it's an expression that involves things like the width of this Gaussian, for example. The wider it is, the lower the capacity. Now, Shannon, in a very famous result known as Shannon's theorem, related the notion of channel capacity and bit error probability in a way that tells us and defines an extremely sharp boundary between codes that are feasible and codes that are infeasible. So let's look at the diagram. The x-axis is the rate of the code. Remember, the rate was k over n in the example that we gave. And this is a rate in multiples of channel capacity. So this says, once you define the channel capacity, we can look at the rate of a code, and each code will try for could be in a different point on the spectrum in terms of the rate. On this axis, we have the bit error probability. So obviously lower is better in terms of bit error probability. And what Shannon proved is that this region over here, the region that I'm marking here in blue, the attainable region, is you could construct codes that achieve any point in this space. That is, for any point in this two-dimensional space of rate and bit error probability, you could achieve that, you can construct a code. He didn't show it as a constructive argument. It was a non-constructive argument, but he proved that there existed such codes. Conversely, he showed that anything that passes on this side of the boundary, the forbidden region, is just not attainable. That is, no matter how clever of a coding theorist you are, you could not construct a code that had a rate above a certain value and bit error probability that was below a certain value, which is the shape of this boundary that we see over here. And you can see why the channel capacity is called capacity, because this is a multiple of 1. So this was Shannon's theorem, and it's set up, as we said, a non-constructive proof that the blue region was an attainable region, but the question is, how can you achieve something that's close to the Shannon limit, as known? And around up to a certain point in time, the mid-90s, this was sort of a diagram of the kind of what was achievable in terms of codes. And so this is a diagram we'll see several times from in a minute. So here is, on the x-axis, we have the signal to noise ratio measured in dB, and on the y-axis, we have the log of the bit error probability. And what you see here are codes that were used. First up here, we see the uncoded version, and you can see that the uncoded is not very good. It has very high bit error rates, so higher here is worse bit error rates, so very bad. And of course, as the signal to noise ratio moves to the left, the error rate grows. And what you see over here in these two other lines are the bit error rates, sorry, the curves achieved by two of the NASA space missions, Voyager and Cassini. And you can see that there was a good improvement between Voyager and Cassini, because 1977 to 2004. And then in May 1993, a revolution happened in coding theory. And this was a paper by Baru et al. And you can read the title of the paper. It was a shocking title. It says, "Near Shannon Limit Error Correcting Codes." And they called this turbo codes. they tried to submit this paper, people didn't believe them that this was possible because this was so much better than any of the previous codes that had been proposed. And people said, no, this can't possibly be the case. And then they checked it, and it turned out that, in fact, their code worked, but nobody really understood why. Okay, so now you might wonder, well, why the heck am I telling you all this? What does it have to do with probabilistic graphical models? Oops. Sorry, we have to scratch that. So why was this so surprising? Because if you look at the turbo codes in terms of this diagram that I showed you a minute ago, you can see that over here we have, again, this is, remember, the uncoded. This is the same kind of diagram, signal to noise on the x-axis, log bit error probability on the y-axis. Here, once again, we have Voyager and Cassini there. And look at the turbo codes. The turbo codes are way to the left of any of these previous codes. Now, again, remember, left is better. Left means that you're achieving the same bit error probability with a higher signal to noise ratio. So what is the magic of turbo codes? And this is where we bring ourselves back to probabilistic graphical models. Because you might be sitting there thinking, well, you know, fine, coding theory is great, but this is the coding theory class, so what does this have to do with probabilistic graphical models? So to understand that, let's look at what turbo codes do. So turbo codes took the same set of bits that we want to transmit, U1 up to UK, and they passed them through two encoders, encoder 1 and encoder 2. And then those bits were passed through our noisy channel over here, so that what we get at the end is noisy versions of those two sets of bits. And what we'd like to do, really, coding is a probabilistic inference problem when you think about it. Because what it's trying to do is it's trying to compute a probability distribution over the message bits, given my noisy evidence, Y1 and Y2, which are the noisy bits that I received on the channel. But instead of trying to solve this probabilistic inference problem exactly, what Brew et al. Proposed in this turbo coding paper is this sort of iterative approach, where we have a decoder that matches the first encoder. So decoder 1 matches encoder 1, and decoder 1 takes these noisy bits that you get from encoder 1 after they pass through the noisy channel, and decoder 2 gets a separate set of bits, the bits that were passed through encoder 2 and then the noisy channel. And what happens, roughly speaking, in turbo codes is that the two decoders start to communicate with each other. So decoder 1 looks at its bits, and it doesn't exactly know what the correct bits are, but it computes a posterior over those noisy bits. And it takes the posterior over each of the noisy bits, and it passes it to decoder 2, which now uses it as a prior over the values of these target bits, the U, combines it with the evidence from the noisy bits Y, and now computes a more informed posterior over the U's, which it then sends to decoder 1. And this process continues to iterate until convergence. So each decoder computes a posterior and passes it to the other decoder, which uses it as a prior. And if you look at the implications of this iterative algorithm, what happens, so you can see here are the different values for turbo decoding. And what you see here, again, is the signal to noise ratio on the x-axis, the log bit error probability on the y-axis. And you can see that initially, in the first iteration of turbo decoding, the curve is not that great. But then as the iterations improve, the bit error rate goes down. So, for example, for a fixed signal to noise ratio, say here, the bit error rate goes down from here to here over iterations. And what you see is as the dark line at the bottom is the optimum bit decision if we were to do correct probabilistic inference. And so the surprising part was how close this totally heuristic and unmotivated algorithm, as it seemed at the time, comes to the optimum of the bit decision. The revolution that happened in this field came up when other people realized, people like Michaelis and Mackay and Frey realized that what was really going on here is that this algorithm that we saw over here is running a variant of loopy belief propagation. Because what's going on here is that each of these decoders is actually running exact inference over a network that is sort of tractable. And then it's passing messages. These beliefs that are being passed are what we had as the delta ij's between, in this case, these two components. Really what was going on here are two decoders that are communicating with each other via a process that is exactly identical to loopy belief propagation. And this caused a revolution in the field in two different ways. Actually, it caused a revolution in two different fields. It caused a revolution in the field of probabilistic graphical models, because up until that point, people had known that you could pass loopy messages over the graph. In fact, this was an observation that was made as early as 1988 by Judea Pearl when he wrote the seminal book that really introduced Bayesian networks to the field of artificial intelligence. And he wrote at the time that sure, you can pass these messages over this loopy graph, but you have no guarantees of convergence, and you have no guarantees that this gets the right answers, and so it's not perhaps a good idea. And from 1988 until the mid-1990s, the algorithm had been completely abandoned because people said that it had these limitations, and so it wasn't a good idea. But when people realized that in the context of coding theory, this algorithm, which is obviously heuristic and has all these potential limitations, nevertheless succeeds in achieving performance that looks like this, then people said, wait a minute, if it works so well for decoding, maybe it's a good algorithm to think about after all. And from the mid-1990s until today, this set up a huge amount of work in the field of probabilistic graphical models on understanding when and why loopy belief propagation works, as well as constructing improved versions of loopy belief propagations, some of which we briefly mentioned in this course. So that's the first revolution. The second revolution occurred in the field of coding theory, where people said, well, if all that's going on is that we're running loopy belief propagation over a graph that is trying to compute the posterior over the U's, the message bits, given the noisy bits, the Y's, well, we can construct lots of other codes and use those codes and run loopy belief propagation on the resulting graph. And sure enough, some of the more successful codes that are in use today are in fact not necessarily the turbo codes that Baru et al. Originally came up with, but a class of codes called low density parity checking codes that are actually really good and elegant match to loopy belief propagation. Now it turns out parity checking codes were actually invented by Robert Gallagher in 1962. And since 1962 up until sort of the late 90s, they had been totally abandoned because they were computationally intractable to do in terms of exact probabilistic inference. But by realizing that one could run loopy belief propagation as a way of decoding using these codes, that reintroduced the codes into the field, and now they're wildly successful, and there's all sorts of variations on them and extensions and so on. So what are these parity checking codes? So in a parity checking code, we're actually sending two types of bits. So if these are our original bits U1 up to U4, the original set of bits are just, the first set of bits are just the original message bits. So I denoted them here, even though X1 is actually identical to U1, I just wanted to denote specifically X1 as the sent bit. So X1 is just a copy of U1, X4 is a copy of U4, and once again, the Ys are the noisy bits that are received. after transmission. On the other side, the X's that you see here on the bottom are parity bits. Parity bits are like checksums on a file. They look at bits and they compute different parity of different subsets of the bits. So X5 here is the parity, that is whether even or odd, 0 if even and 1 if odd, of U1, U2, and U3. You can see U1, U2, and U3. X6 tests the parity of a different set of bits, U1, U2, and U4, and X7 does U2, U3, and U4. So here we're sending 4 original bits and 3 parity bits. So this in total is a code whose rate is 4/7 because there's 7 bits sent, of which 4 are message bits, or 4 message bits. And when you think about this, this really lends itself beautifully to a belief propagation algorithm because you have these factors over here, this factor over U1, U2, U3, and the received bit Y5. And so messages are passed over a graph of a given distribution that has these factors associated with it, as well as the factors over the singletons, U1 up to U4 separately, relative to their evidence, Y1 up to Y4 separately. And so decoding is now done as loopy belief propagation, where we have, as we said, the U1 cluster, U2, U3, and U4. These are my singleton clusters. And then these are the large factors. And some of you will recognize this as a beta cluster graph, beta structured cluster graph. And so this is just a list of applications. This is probably one of the most ubiquitous applications of probabilistic graphical models in use today, simply because it exists in so many instantiations of, in many set-top boxes, and when you're doing digital video broadcasting, in communications of mobile television, mobile telephones, to satellites, NASA missions, wireless networks, and so on. So one of the really powerful applications of loopy belief propagation and probabilistic graphical models that arose from this unexpected confluence of these two disciplines. So really, you could say that loopy belief propagation, which was originally discovered or proposed by Judah-Perl in 1988, was actually rediscovered by practitioners of coding theory. These were not theoreticians of coding theory. These were people who actually sat down and engineered codes. And understanding those turbo codes in terms of loopy belief propagation, and that was done by a bunch of more machine learning and information theory type people, led to the development of many new and better codes. And the current codes are actually coming gradually closer and closer to the Shannon limit in a constructive as opposed to a theoretical way. And at the same time, the resurgence of interest in belief propagation led us to much of the work that we see today in approximate inference and graphical models, as well as both on the theoretical understanding side, as well as on new algorithms that people are coming up with derived from that new understanding.
หาอะไรนะ sum product กับ max sum อยู่ตรงไหนหาไม่เจอ ลืมไปแล้วอะ sum product กับ max sum sum product กับ compute initial potential ก่อนนะ 9 คูณ 9 ก็คลิกเชื่อมกัน adjacency matrix แล้วก็ result คลิก list อันแรกเป็น 17 ได้ phenotype ไหม phenotype ของคุณพ่อคูณกันเรียบร้อยก็ได้เป็นแฟกเตอร์ทั้งหมดที่ถูกใส่เข้าไปในคลิกนี้ไม่แน่ใจว่ามีอะไรบ้างก็คงมี17คงมีอันนี้เส้นนี้แน่ๆ1มีไหมไม่แน่ใจต้องไปดูกัน17อาจจะมี1ก็ได้คิดว่ามีไหมจากตรงนี้มันควรจะมีแค่ฟีโนไทป์มันควรจะมีแค่จากฟีโนไทป์มา3อันใช่ไหมแล้วก็ออกมาเป็นฟีโนไทป์เหมือนให้โดนคูณกันนะตัวนี้คูณตัวนี้ได้อันนี้คูณอันนี้ได้อันนี้คูณอันนี้ได้อันนี้ก็มาจากอันนี้คูณอันนี้ได้อันนี้ก็เป็นแฟกเตอร์โปรดักต์ธรรมดาไม่น่ามีอะไรเปลี่ยนจาก71เป็น17แต่เรียงลำดับไม่มีความหมายอะไรมีความหมายสำหรับของเรานะไม่มีความหมายอะไรถ้าเราเรียงอันนี้กับอันนี้ถูกโอเค initial product compute initial potential take the click T skeleton 4 node 8 factor list เหมือนเมื่อกี้ที่ดูมา return standard form of a click 3p มี click list กับ edge compute assignment of factor to click ยากแฮะไม่ธรรมดาเราจะทำยังไงให้อันนี้อันนี้คือเป็นโครงคือสเกเลตันของคลีอยู่แล้วมันก็จะให้มาแล้วว่ามี1 7 2 8 3 9 4 10 5 11 6 12 1 3 4 1 2 3 2 5 6แล้วก็ h อันเนี้ยจะเหมือนกับ h อันนี้เลยเพราะมันคือโครงสร้างเดียวกันส่วนตัวอันนี้ก็ขึ้นกับเราจะ assign factor list 12 อันนี้เข้าไปในอันนี้ยังไงเขียนยังไง MATLAB ลืมหมดแล้ว input factor list ว่า input node เรามีฟังก์ชันอะไรช่วยไหม โอเควางแผนว่ายังไงบ้างวางแผนว่าจะ assign ทั้งหมดจัดเรียงลำดับตามสเกเลตันมันสมมตินี่เป็นสเกเลตันแล้วก็ไล่โหนดไปเรื่อยๆโหนดแรกแล้วก็จัดเอาทั้งหมดนี้ใส่เข้าไปในนี้แล้วก็คูณ factor product ทำให้เรียบร้อยมันก็จะได้อันนี้ซึ่งจะเป็น struct แบบ factor ธรรมดา1 อันเสร็จแล้วก็ไล่มา28แล้วก็ดูว่ามีอะไรบ้างที่มี2และ8ก็มี8 2อันเดียวเนาะ2ไม่มีโอเค2ไม่มีต่อไปก็39ไล่39ก็มี93แล้วก็มี3ด้วยก็เอา3กับ93ใส่เข้ามาโอเคก็ต้อง for loop อันนี้กับ for loop อันนี้แล้วก็จัดเข้าไปในตัว result เราก็มี2 อัน p click list อันนี้โอเคนะมีทั้งหมดก็เท่ากับจำนวนโหนดจำนวน n โหนดเล left match นี่มันคือยังไงนะนี่คือ row หรือ column ไม่รู้นะลองดูดิ9 row ฮะเสร็จแล้วเราก็ได้ ph แล้วแน่ๆ ph ไม่มีอะไรคือตัวเดิมของ c dot ต้องชื่ออะไรนะ h เหมือนกันนะเพราะมันเป็นโครงเดียวกันส่วน p click list เนี่ยเราก็ใช้ for loop ไป for loop เขียนยังไง ลืมแล้วอะลืมจริงๆนะเนี่ยเขียนไงวะ affect button มี for loop ให้ดูไหมนี่น่าจะมีไม่มีเว้ยno for i เท่ากับ1โอเคเรียกความทรงจำกลับมาเขียน r อยู่อาทิตย์หนึ่งกลับมาแล้วงงเลยหมดแล้วจินตนาการแป๊บหนึ่งทำยังไงให้มันค่าตรงกันอันนี้คืออะไรนะต้องเป็นอย่างนี้นะนี่คือ list โอเคอันนี้มันคือ list มันมีlist สมมุติถ้ามี list 2 อันต้องชื่อว่า b แล้วกัน b 2อย่างนี้ได้ไหมได้ b 1 2นี้ได้ไหมไม่มีเนาะยังไงนะ b 2MATLAB select object in list มันคือเรียกว่า list ใช่ไหมarray MATLAB selected from array object array indexing หรือว่าใช้อันนี้โอเคนะ b โอเคใช้เป็น bracket ก็คือเป็น bracket เหมือนกันนะb 2 1โอเค1โอเคฮะนี่ใส่นี่เข้าไป i เท่ากับ1ถึงn ฮะใส่ n เข้าไปก่อนเลยแล้วกันนะมันมีอันอินไหมเนี่ยสมมติ3อิน3 4มีเนาะลืมหมดเลยเกิดอะไรขึ้นเรามาดูที่เราเคยเขียนไว้ดีกว่ามีคำว่าไฟล์